do a few problems involving integration by parts. Remember that our formula here is that integral of u dv equals uv minus v du. So refresh yourself in the previous video if you need to kind of get back up to speed on the process there. Our first integral is the integral of x times natural log of x dx. So let's see if we can't figure this thing out. Maybe we can apply some techniques. So we have to pick, when we're filling this out, we have to say, all right, which thing is u and which thing is dv? So I have to say, which is u and which is dv? Now, by doing this is important because the choices you make here are going to influence here, and we're going to have to determine whether or not we did this right. So I'm going to say, all right, u. Well, what we want to do typically is pick something that makes your life a little easier when you take its derivative or antiderivative. So what I might say is, okay, well, u is going to be x, because clearly du equals dx. It makes my life a lot simpler if I go that way. Now, if I take dv to be natural log of x dx, then I have to figure out what the antiderivative of natural log of x is. And sadly, we haven't covered that yet. In fact, that's what we're going to cover in this next piece. So it's not an ideal candidate for what we're trying to do. So instead, this is probably not the right way to do it. So let's try the other way. So I'm going to pick u to be the natural log of x. So du is 1 over x dx. Now that's not much more complicated. I wouldn't necessarily call it, I actually would call it easier. It's nice when you have things in terms of powers of x versus natural logs or e's or something like that. And dv is going to be x dx. So again, remember we take whatever's left, and the d's should always match. du, dx, dv, dx. So then we take the antiderivative of x. Well, the antiderivative of x is 1/2 x squared. Okay? So now that we have those, let's see if we can't put these together. We need to follow the pattern. So u dv equals uv minus v du. So let's fill these in with every piece that we have. We have u, so that's natural log of x, and we have dv, x dx. So one of the reasons we do that we don't really have to write it, we have it here, but we're trying to make sure that we've covered every little piece. If you have very large expressions, not just something with just two little functions there, if you have very large expressions, it's important that you write this out so that you make sure that you've covered everything, that you've actually captured your whole problem. So now when we fill this out, we have u, v, so that's, I'm going to in fact write this part first, that's 1/2 x squared natural log of x. So I'm really writing vu, but it doesn't matter, minus, now we have v, that's 1/2 x squared, and we have du, 1 over x dx. So I'm kind of bleeding over into this little space here, but we'll be okay. Now what I notice here is that I have x squared and I have 1 over x. So that's nice. That's going to have some cancellation here. That's going to give me, let me move. That's going to give me 1/2 x dx. Well, we know how to take the antiderivative of x, so I get 1/2 x squared natural log of x minus 1/4 x squared plus c. Now another way you may write this isn't necessary, but you could factor out a 1/4 x squared and you would get 2 natural log of x minus 1 plus c. That may or may not be helpful. One thing you might want to do as well is take the derivative to verify you've done this correctly. A big problem with integration by parts is it can be hard to understand whether you've done it correctly. So let's take an antiderivative here. Or sorry, take a regular derivative here. If I take the derivative of this, then by the product rule, I get 1/2 x 2 natural log x minus 1 plus 1/4 x squared 2 over x. And then the c goes away. So this, again, this is the derivative piece. So then if I distribute this, those cancel. I get x natural log of x minus 1/2 x. And then that 2 cancels with that to get a positive 1/2. Those cancel. So these also cancel. And I'm left with x natural log of x. So since the derivative of my antiderivative is what I started with, I can be reasonably confident I've done this correctly. That's kind of an important self-check piece. All right, let's move on. Let's move on to natural log of x dx. So this one's a little tricky because you're like, okay, well, I've got to have a u and a dv, but I've only got one thing here. In fact, if you didn't know to use integration by parts, you might not know what to do at all. But since we're dealing with integration by parts, let's try some stuff out. I'm going to say I'm going to take u to be the natural log of x. I'm going to say, okay. So the only thing left over for dv is dx. So the antiderivative of dx is just 1. Right? Not 1, it's x. Right? Because the derivative of x is 1 dx. So if you had an integral of just dx, that would antiderive to x plus c. And so then we have du here. Well, the derivative of natural log is 1 over x. So I have 1 over x dx. So now we can follow the pattern. We can say, okay, u dv equals uv minus integral v du. Okay, let's fill it in. U dv, so natural log of x dx equals uv, so natural log of x times x, so I'm going to write that as x natural log of x, minus, we have the integral of v du, so that's x, 1 over x dx. So x times 1 over x just cancels to become 1. And again, the integral of dx is just x. So we have x natural log of x minus x plus c. That's typically the way you'll see that one written. You could also write it as that's less common, but it is there. So that's how we get the integral of natural log of x. It's a pretty useful one. You'll see the integral of natural log of x come up a decent amount, so just kind of be aware that that's going to be there. All right, finally, we have x squared e to the x dx. So in this particular case, we just have to pick u and dv and kind of keep going. So yeah, it's supposed to be purple, but that sure does show up a lot like black. Well, we'll just keep going. It'll be all right. So u and dv, and then du and v. So which one do we pick? Well, generally speaking, you're going to pick the ones that make your lives easier. So if u is equal to the polynomial, then when we take the derivative, we're going to get 2x dx. And when we take the antiderivative of e to the x dx, we get e to the x. So again, we didn't get anything more complicated, and this one became more straightforward. So that tells us we're on the right track. So let's fill this thing out. So now filling that out, x squared e to the x minus So v is e to the x, du is 2x dx. So I'm going to rewrite this as 2x e to the x dx. Okay, so we have an issue here. We have an issue because 2x e to the x itself is not, it's not directly integrable, right? This was directly integrable. This was directly integrable. This is going to require you to use integration by parts again. So what we have to do is we have to sort of take a step and we have to say, okay, all right, let's just look at just this piece here. Sort of like a sub-problem. We're going to break it into a sub-problem. Think of it almost kind of like the way you do if you were doing computer programming or something. You break it into big problems and then into smaller chunks. So let's just, for a moment, analyze this. Two x e to the x dx. So then I would pick u to be 2x dv e to the x dx so du is 2 dx and v is e to the x. So then we fill this thing out. We say, okay, 2x e to the x dx. In the interest of space, I'm not writing this. I normally would. I strongly recommend it, but there's only so much board left. So that's u dv equals uv, so 2x e to the x minus integral of v du. So that's 2 e to the x dx. Now this is directly integrable, right? The 2 can just come out, not a problem. And the antiderivative of e to the x dx is e to the x. So I get 2x e to the x minus 2 e to the x plus c. So then what I do is I take this piece and I plug it in up here. So I have x squared e to the x dx minus everything that's here. 2x e to the x minus 2. So because I had that minus, I have to subtract everything that's here. That gets me x squared e to the x minus 2x e to the x minus 2, or sorry, plus 2 e to the x plus c. Now you might ask yourself, why is that not minus c? Because that was a minus and that's a plus c. The answer is it doesn't matter. C is an arbitrary constant. C could be positive, it could be negative, it could be anything. Really what you're saying here is that we're adding on some number. So if that's equivalent to say we're subtracting some number, because subtracting in some negative number would be like adding some positive number. So by convention, we typically, unless we have a very good reason, and there are good reasons, but unless we have a very good reason, we write that as plus c no matter what, no matter how the arithmetic shakes out, because it's arbitrary, it's not fixed. So that's kind of an introduction to integration by parts. We're going to do more examples, and hopefully that'll give you a little better understanding of what we're doing.